Welcome everyone. Thank you so much for your time and joining us today as we share and explore the findings of the second scale of the PYROCO plant trial that we have been collaborating together with RMIT and Iota and other partners. Before I go any further, I'd like to acknowledge the country that we are coming from. We are coming today from the lands of the Bunurong people of the Kulin Nation. We are located in the southeastern suburbs of metropolitan Melbourne, and so we acknowledge their ownership of the lands and the waterways of which we are on and which we have the privilege to work on. We acknowledge Torres Strait Islands and Aboriginal peoples that may be joining with us today and acknowledge their leaders, past, present and emerging. So thank you so much for joining us again. Today, I will just quickly introduce the flow of the session that we are going to go through. Our first speaker today, Aravind Surapanini, he will briefly describe the context and the broader issues for biosolids management, particularly as that we are facing in Victoria. Secondly, then we will pass on to Professor Kalpit Shah from RMIT University. He will be describing for us the PYROCO technology and the specific benefits of that technology. Then I'll pick up the story for a while and describe the results and learnings from our second scale of pilot plant trial back in November. And then Eamon Casey will bring us home and describe further a recap on the business case and the commercial pathway of potentially for biochar and the market opportunities associated with it. So that's our basic flow for the day. I'll also note we do have a Q&A function down the bottom of your screen. Please feel free to add your questions there. The panelists may, if they have the opportunity, try and answer those during the session. If not, we'll try and get back to those at the end of the session, and we should have enough time to do that. So we will just really quickly introduce ourselves before we start moving into the content. So my name's David Bergman. I'm the facilitator for the day, and also I am the Research Development and Innovation Manager at Southeast Water. I oversee a broad portfolio of research projects, really looking at the long-term needs and problems to solve for Southeast Water. And in this particular project, we've been collaborating with RMIT since back in 2017. I will pass over to Aravind to briefly introduce himself.
Thanks, David. I'm Aravind Surapanini. I'm the Principal Scientist of Biosolids at Southeast Water, but I'm also the Deputy Director Industry for the ARC Transforming Biosolids Center based at RMIT Bandura campus.
Thank you, Aravind. Kalpit, you want to introduce yourself?
Hi, everyone. I'm Kalpit Shah. I'm a professor and Deputy Head Research of Chemical and Environmental Engineering Department at RMIT University. I'm also one of the Deputy Directors Research for Biosolids Training Center, funded by Australian Research Council. And I also lead a small group called Innovative Resource and Waste Technologies Research Group at RMIT University. I'm one of the inventors of the PYROCO technology. Thank you, David.
Thank you, Kalpit. And Eamon, can you introduce yourself?
Thanks, David. Hello, everybody. I'm Eamon Casey. I'm the Technical Director of Iota. I'm a civil engineer with about 28 years experience in the water sector. And for those who don't know Iota is the commercial arm of Southeast Water. So we commercialize IP generated in Southeast Water. And in this case, we're going to be the commercialization partner for PYROCO with RMIT. Thanks, David.
Thank you, Eamon, and thank you to all our panelists today in advance. So our first speaker for today is Aravind. He is going to broadly set the context for biosolids management within the water utility context, and is going to also explain a little bit about our journey into PYROCO and biochar. Aravind, over to you.
Thanks, David. Good afternoon, everybody on the call. And yeah, my 5-minute spiel is going to be on the introduction. So biosolids contain nutrients, notably nitrogen and phosphorus, which are critical for plant growth and are often lacking in agricultural soils. And for this reason, beneficial use in agriculture is the most preferred option for most utilities so far. Currently, in Australia, 70% of biosolids are used in agriculture, as we all know. Like most other utilities, Southeast Water has mastered agricultural land application route for biosolids over the last 20 years. And we do it really well. The application rates are, however, based on meeting 100% nutrient requirements. What this means is there is no need for our biosolids customers to buy commercial nitrogen and phosphorus fertilizers. They all love biosolids. However, regulatory environment in biosolids space is rapidly changing. Conventional contaminants in most biosolids guidelines include heavy metals and organochlorine compounds. But as we all know, there are other contaminants of concern like PFAS, microplastic, and pharmaceuticals in biosolids. Regulators now began to give more stringent advice on PFAS, not only in Australia, but also across all developed countries. New South Wales EPI recently included galoxolide and triclosan in their biosolids regulatory review. So there are other emerging contaminants as well. In 2021, our EPI in Victoria directed our Victorian water companies to follow end of the waste code biosolids in Queensland with PFAS soil trigger values. With our current application rates, soil PFAS levels after biosolids application are likely to exceed this guideline soil trigger values in both Queensland end of the waste biosolids guidelines as well as the draft NEM 3. Most of you know NEM, National Environmental Management Plan 3 is in the draft. Most of you have seen it. So NEM 3 is expected to be cleared by ministers from all governments by end of the year. So fortunately, we began our biosolids to biochar journey with RMIT back in 2015 with a couple of master's projects. These two master's projects generated biochar from our biosolids, and the biochar data gave us a lot of confidence in the biochar properties as a plan B option. So this master's project led to a major R&D project with RMIT and Intelligent Water Networks on RMIT patented PYROCO technology, as David said, is back in 2017. We basically used a bottom approach. A series of studies were undertaken based on industry insights and laboratory experiments to study biosolids pyrolysis at multiple scales. So Mark I pilot plant trials with Southeast Water biosolids was successfully completed in 2021. This showing no PFAS in the biochar. This Mark I plant was conducted at the Irrigation Water site at Melton. Following on our success with Mark I pilot plant, we built and operated Mark II plant in 2023 with funding from state government, Intelligent Water Networks, and a few Victorian water utilities. Mark II is a significant upgrade from Mark I, and Kalpit will describe how the PYROCO technology works. Mark II pilot plant trials used 6 feedstocks, 5 biosolids feedstocks, and 1 food organics and garden organics feedstock. And David will talk about this Mark II trials, some results as well. Both Mark I and Mark II trials were conducted at as I said, at Western Water site at Melton, and we really appreciated their support, their ongoing support with this PYROCO Mark I and Mark II trials. Also, Mark II trials generated interest from water utilities across Australia, 4 within Victoria and 4 outside Victoria. If they all come on board, we're going to operate Mark II plant in the next few months. As I said, 4 from Victoria and 4 from outside Victoria. So finally, a need to move forward quickly and deliberately on a biochar route is becoming more imperative for all of us, across, and not only in Australia, but also across the developed nations, will make farmers fall in love with biochar too. Now, I will pass back to David and looking forward to questions later.
Thanks so much, Aravind, for setting the scene there for us. I'll just remind everyone that the Q&A is available, so please don't hesitate at all to put any kind of question in there. We'll try and add to those questions or answer those questions as the panel goes on, and we'll get to those at the end, so please do that. So thank you again, Aravind, for setting the scene for us. I'm going to pass over now to Professor Kalpit Shah, who's going to really explain more how the pyrolysis technology works and the particular benefits of the technology and why we're pursuing this direction. Thank you so much, Kalpit.
Thank you, David, and thanks, Aravind, for nice introduction. Now, I'll take you guys through how PYROCO works. So what is first PYROCO? So PYROCO is a fluidized bed heat exchanger device. So what we have done is we have converted a conventional fluidized bed system into a fluidized bed heat exchanger type device, which offers significant benefits. So I'll talk about the benefits later, but let's see how PYROCO works. So in PYROCO, pyrolysis occurs in a pyrolysis zone, which is the most inner zone of the PYROCO system, as shown here. So imagine you have a reactor and a distributor plate at the bottom, and then you have a fluidizing gas constantly coming from the bottom, and your solid waste like biosolids, you're constantly feeding from the top. Now, with the help of fluidizing gas, your solid waste, or in this case, biosolids, will be constantly fluidizing at given temperature. But this fluidizing gas will be oxygen-free. That's why you're creating pyrolysis type environment. Now, when pyrolysis occurs, your biosolids produce mainly oil and gas vapors as well as biochar. Biochar will stay in the bed within the reactor. However, oil and gas vapors will travel upwards, and then we have created at the top a screen type disengagement zone through which we're taking the oil and gas vapors out into an adjacent combustion chamber, where with the tangential air inlet, we're trying to combust some of the oil and gas vapors in the adjacent combustion zone. Now, when partial oxidation of these oil and gas vapors occur, they generate energy, and this energy will be provided via indirect mode to the pyrolyzer, because pyrolysis of biosolids is an endothermic reaction. Now, imagine if you don't have sufficient surface area available just outside the pyrolyzer reactor through just the peripheral surface area, then what we're creating additional surface area by putting some of the tubes inside the PYROCO reactor and allowing the combustion gases traveling upward all the way to the out of the reactor. And this then flue gas could go to the thermal oxidizer followed by dryer. Now, biochar will be constantly taken out from the pyrolyzer via an overflow or underflow discharge screw. So imagine you have constant biosolids you're feeding, constant pyrolysis is occurring, and also you have a constant discharge of biochar, and oil and gas vapors which are consistently produced, taken out into a combustor and partially oxidized, and they're traveling through tubes all the way up and out to the reactor. So these combustion gases are providing energy for the pyrolysis reaction. Now, let's see what benefit PYROCO offers. So what we have done, the first thing we've done is we have overcome the heat transfer surface area limitations in any other conventional or emerging reactor designs by converting fluidized bed into a fluidized bed heat exchanger type device. So for any other reactor, what surface area you will have available is just the peripheral surface area of the reactor itself, where pyrolysis would occur. Now, in pyrolysis, along with that additional peripheral surface area, you could add more surface area by adding number of tubes within the PYROCO reactor. So that way, if there is highly endothermic pyrolysis reactions occurring, you could actually, with scale up, you could still meet the surface heat transfer surface area requirement. Then second thing that we have overcome is we have overcome the heat and mass transfer limitations associated with other conventional or emerging reactor designs. They have mixing problem, and hence they may have lower heat and mass transfer coefficients. In our design, particularly with fluidized bed and addition of these tubes, we're significantly improving heat and mass transfer. Now, what is the benefit of improving heat and mass transfer? With the heat and mass transfer improvement, you can achieve constant or uniform temperature within the pyrolysis zone, and hence you can get consistent high quality or consistent quality product, that is biochar. So imagine if you have contaminants, then you all want to make sure that the contaminants are safely removed from all biosolids. And that's where uniform temperature in the bed or in the reactor will surely help. The third important part that we looked at is, while designing the reactor, is it's easy to fabricate and maintain. So the reactor is simply made up of tubes and pipes, and you could easily take them out, the tube bundle out, just by opening up the top flanges, clean it inside, and do a pressure clean of tubes, and put them all back with just through a flange. So it's much easier to fabricate and also much easier to operate and maintain. Also, in our design, the important part that we did is the temperature difference between our pyrolysis and adjacent combustor is not high. It's only 150 degrees centigrade. When you have lower temperature differences, you could use lower cost or less expensive materials for constructing inner side of the PYROCO. So in our case, we will be mostly using SS310. Stainless steel 310 grade, in contrast to Inconel, which are mostly used by many other designs. And Inconel cost 3 times more than SS310. So that's how we're going to reduce capital cost by avoiding use of expensive materials for construction. Now, another thing is the PYROCO doesn't have any moving part. Like in auger or in multi-hearth, you will always have moving part sitting in the hot zone. Now, this moving part will face constant thermal expansion and contraction when you start up and shut down, and will lose their life much earlier. In PYROCO, we have avoided any moving part within the hot zone. That's why we think that it will not only reduce the maintenance cost, but it will also improve the plant availability as well. And the last thing is, while developing this design, we constantly question ourselves that currently available commercial or emerging designs could only offer up to certain kilograms per hour capacity. And after that, they provide modularized units. Now with that, you can't achieve economy of scale benefit. So with PYROCO, we're hoping to cater various demands from a small to medium size all the way up to large scale in a single unit. And that will surely improve the cost benefits, because you could, if you have one large reactor, you will save a lot on capital as well as other operating costs. I'll stop there. Over to you, David.
Thank you so much, Kalpit, for taking us through the technology and the process. The Q&A is now open. It appears perhaps initially it was disabled, but that now function is working well. So starting to see the questions coming through, which is fantastic. Some of the panelists will hopefully have a go at answering some of those, and we'll come back to some of those at the end. And I can see already we will hopefully be answering a number of them in the remaining part of the webinar. So thank you so much, Kalpit. So this is where I pick up the story in terms of back in November last year, 2023, with the help of some funding from the Victorian Higher Education Scheme, as well as DECA, so that's the Victorian Department of Energy, Environment and Climate Action, we built the second scale of pilot plant. You can see a picture on the screen there. So by I mean RMIT in collaboration with South East Water, but in particular with Round Hill Engineering, who've both been on the journey at the different scales of putting this technology together since 2017. And the experience that both these teams have in terms of reactors, high temperature processing, as well, has been invaluable to the scaling process. So back in November, we ran across a period of about 2 weeks. We were operating at about 20 kilos per hour of biosolids feedstocks. That's equivalent to about 85% solids at that dry basis. So fairly low rates at this point in terms of the scale. But you can still see the scale of the pilot plant, still significant. It's no longer a toy. So we ran a mix of biosolids. We also then ran mixtures of biosolids and straw, and we also ran AFOGO, food organic, garden organic material as well. These materials were sourced from a range of metropolitan water utilities and regional water utilities. Some were in a granule form, about 1 to 2 millimeters in size. Others were in a pelletized form, about 4 to 20 millimeters in size. And overall, we ran, I think Aravind mentioned this already, about 6 forms of biosolids and FOGO through the pilot plant at that point in time. So it was, considering the time that we had, it was a good range to be able to put the PYROCO reactor to the test. As I can see, it's come up in a question here. This is just the reactor side. The biosolids were dried separately at this point in time, and we'll touch on that later. So in building the Mark II, we took a range of learnings from the previous scale of Mark I, and a number of improvements were made. I'll touch on 2 significant ones, most notable ones. And first one was the way that the gas producer and the PYROCO reactor are integrated. So the gas producer takes biosolids also in more of a combustion type process to produce the syngas, and that syngas is the fluidizing gas of the fluidized bed of the PYROCO reactor. And that is then integrated in a feed rate sense and temperature control sense with the PYROCO reactor itself. So basically, biosolids is the fuel and the raw material all at the same time because of its calorific value. The second most notable inclusion is the multiple sampling points that were put into this pilot scale reactor for emissions testing, and I can see some questions coming up around that in the Q&A, which is great. Most particularly, we wanted to focus on PFAS in the emissions and in the biosolids and in the waste. So talking about PFAS, our lab studies in our previous scale had already shown us that PFAS through pyrolysis could be removed from the biosolids, which is great news. PFAS-free biochar for its future applications is a great outcome. But at the time and at the scale, we weren't set up to prove that the PFAS was actually destroyed at that point. So that was a key outcome we were after in this second pilot plant scale. So in this scale, we added a thermal oxidizer at the end of the process, which is well understood and well established technology that when run at greater than 850 Celsius and for longer than 2 seconds contact time, that PFAS should be destroyed under those conditions. And so we were confident with that at the end of the process, even if we hadn't been able to reduce it through the process, that would be destroyed through the use of the thermal oxidizer. We also want to explore the fate of the PFAS from the biosolids through the process, make sure it was destroyed or see where it ended up. And so if we couldn't detect PFAS at any of these points in the process, that's pretty strong evidence that we were breaking it down as part of the process. And that indeed was what we were able to demonstrate through the emissions testing and the sampling, that we couldn't find PFAS other than the source biosolids in the process. So let me explain that a little bit more. So we sampled the biosolids feedstocks before thermal treatment. We sampled the biochars after thermal treatment. We sampled the gases at the exit of the PYROCO system. We sampled the gases at the exit of the thermal oxidizer. We sampled the gases at the exit of the scrubber. And also we sampled the water from the scrubber. And what we found is that, so then they were all our sample points. What we found, that all the biosolids feedstocks coming in, except for the FOGO, did contain PFAS. So in terms of the experiment, that's good news. There's PFAS to begin with. Probably not great news that there is PFAS in biosolids, but we probably all know that. And the PFAS was present there in the range of 4.5 to over 100 milligrams per kilogram. And in the majority of cases, it was actually the PFOS compound that was the predominant compound. What we found then in the final biochars, there was no PFAS detected in those final biochars, which is something we had found before. And the limit of detection, we were down to less than 2.4 milligrams per kilogram as the lower level of detection. The PFAS in gas emissions were tested at various points through the process. So we analysed for 30 species in total. That first process point was at the end of the pyrolysis PYROCO reactor. It was also measured at the end of the thermal oxidizer and finally at the scrubber outlet. And we found that back at the PYROCO reactor, there was still some PFAS present there, although it did appear to be reduced. We did find that there was no PFAS after the thermal oxidizer, which was as to be expected, and then also in the emissions out of the scrubber. There was no PFAS present there either, and also there was no PFAS detected in the scrubber water. So that overall provides pretty good evidence that not being able to detect it in any of those key materials and emissions and waste products, that the PFAS has not just been removed but also destroyed. Having said that, there is some caveats to the process and those kind of claims. Unfortunately, at the scale of the pilot plant, we're still on a relatively small scale, and the subsequent size of pipework and gas flows and locations of the sampling points and positioning of sampling points, we were not able to strictly adhere to the desired US EPA method 13B that we were trying to follow. However, we still, these results are very encouraging, and it will be our plan at the next scale of pilot plant that is larger and will be have much more design intent around being able to achieve that US EPA method. In terms of some of the other biochar characteristics out of the second scale of pilot plant, carbon content, we were really happy with what we were seeing. We're starting off with about 33 to 35% carbon in the biosolids feedstock, and we're ending up with about 31, 32% biochar in carbon in the final biochar. So we're seeing great retention of the carbon, which is really positive for sequestering and carbon trading and credit opportunities as well, and also to be able to use that carbon in the final applications. We also saw the nitrogen and phosphorus present in the biosolids, a reasonable content of that coming through and retained, which will be useful when it comes to future agricultural applications. And also too, we were really happy with the pH of the biochar coming through, which can be modified if required, which with a high pH could potentially be useful in addition to helping with liming in certain soils. Can't really move on here without making a comment about the metals that are present. There are metals present in our biosolids. Those metals are still present in the final biochar. They are in fact concentrated, which is to be expected because we're reducing the volume of the material that we have. Further testing required on this. We do know from previous testing that those metals do appear to be locked within the biochar structure and have low extractability and as a potential proxy for low bioavailability, but this needs further testing in more relevant in-field or accelerated environments. A quick comment on the emissions going ahead, going through this process, other emissions, so SOx and NOx, for example. We added some urea to the thermal oxidizer, which helped with lower levels of NOx, such that they were compliant with relevant EPA guidelines. Similarly, through the pH control in the scrubber water, low levels of SOx were also achieved in those emissions. So in terms of learnings from this process and learnings that we'll look to apply in future scale, we were very happy with the integration of the biosolids-based gas producer with the PYROCO reactor and being able to work those two together to produce the gases for the process and the biochar product as well. We also had some key learnings about the biosolids preparation. As I mentioned, the biosolids were dried and prepared separately to this process that you see on the screen there. That was a very manual, time-consuming, tedious, labour-intensive process that we really don't want to go through again. And it had to be done very carefully because particle size into the PYROCO reactor is the particle that you get out at the end of the fluidized bed process. So we're looking at I'll touch on what we're planning to do around that in a second. Also, too, some of the feed systems need a little bit of optimization, particularly if they're to deal with pellets in the future. Also, the quenching of gases through the process. Looks like we need a scrubber type process to drop the temperature of the gases to improve with fines retention, and also a small cyclone as part of the process for fines retention as well. And also to automation of the way the biochar is removed from the process to support continuous operation. So where we are now actively exploring the purchase of a commercially ready biosolids dryer that we will integrate with the next scale of the PYROCO reactor. In doing so, we're also looking at how we can integrate the waste heat from the PYROCO reactor back into the drying process to overall improve the thermal efficiency of the process, with the goal to be thermally neutral or as close to thermally neutral as possible. And also at the next plan of a demonstration scale, we're calling that, we plan to operate that for extended periods of time with continuous operation as well, so we can gain more information about operations and maintenance costs and requirements around that. So that's a really quick trip through some of the key learnings from the second scale of the PYROCO plant. I'm going to hand over to Eamon now, who will bring us home with a recap of the business case and the commercial pathway and market opportunities. Over to you, Eamon.
Great, thanks, Dave. So today I'm going to touch on 4 topics. I'll start off with the overarching drivers for South East Water, which are the context for the business case that we've had approved. I'll then go into some detail around the business case and the business case pillars that we developed. I shall then talk about the pathway which we have for this technology leading to future commercialization. And I'll close out with a discussion around the biochar market, which we commissioned a biochar report recently. So in terms of the South East Water drivers, all of the utilities in Victoria have been are committed to a net zero by 2035, and that includes quite significant reductions by 2025 and 2030. South East Water has committed to net zero by 2030, and the emissions associated with biosolids, the stockpiling of biosolids, are quite significant. South East Water also has ambitions within the circular economy in Victoria. And in that context, we need to find beneficial use for our biosolids and our recycled water that we produce. And also we want to see at what collaborations we can achieve around circular economy. We've talked to quite a bit. Dave talked quite a bit around the PFAS challenge, and as did Aravind, around the risks associated with biosolids, and that risk challenge very much sits within South East Water with the biosolids that we produce. And then finally, of course, we have customer bills, which we need to keep as low as practicable. So in that context, we developed a business case a number of years back, which was approved, and that business case is going to cover off our next stage of this PYROCO development. The business case had three key pillars. The first was our emissions and net zero. In terms of emissions and net zero, we report the emissions associated with biosolids every year on a system called NGERS to the government. Our Scope 1 emissions associated with biosolids up until recent time stockpile and land application equate to about 1,200 carbon dioxide equivalent tons, based on 6,000 tons of dewatered biosolids that we manage per annum. On the other side of the equation, we'll be sequestering carbon within the biochar. And if we were to convert all of our biosolids to biochar, we'll be generating a carbon sequestration in approximately 1,000 tons of carbon dioxide equivalent. So across both the avoidance of emissions and the carbon sequestration, we're looking at about 2,200 tons of carbon dioxide equivalent, which is about 20% of our wastewater treatment plant emissions, which is quite significant. In terms of PFAS destruction and the risks, the results from our Mark II trial, as we're calling it, as Dave alluded to, were very, very successful. So we're really on the pathway to solving that problem through this PYROCO technology. And then from a financial comparison, we undertook a 25-year net present value comparison. At the time, the cost of our land application, which involved stockpiling for a period of time, a lot of testing, including testing for PFAS, transport and land application, incorporating those biosolids into land, all at South East Water's cost, was running at about just over $200 per ton of dewatered biosolids. That's dewatered biosolids at 50% dry solids equivalent. Looking at a plant scale for South East Water at about 3,000 tons per annum, converting biosolids to biochar. At that scale, which may not be the optimal scale for cost, we're looking at a ballpark between $300 and $400 per biosolids dewatered ton at 50% equivalent. Now we'll need to establish those costs through the next phase of this PYROCO journey, which I'll go into now. But we've got reasonably good detail of what we expect those costs to be from our 2 pilot plants to date. So that takes me into what is our pathway from here. As David alluded to, our next scale up, which we'll call the Mark III, our demonstration plant, will involve a commercial dryer to allow us to run continually. And we're looking at a 5 times scale up to about an equivalent of 1,200 tons of dewatered biosolids per year. And that's dewatered biosolids at 50% dry solids. So that represents about 100 kilograms per hour of dried feedstock into the reactor. We will operate that plant in late 2025, 2026, and that process has started already. As David alluded to, we're looking at dryers as we speak. Beyond that, we're looking at an operational plant, all going well in 27, 28. As I said, for South East Water's treatment plants, probably 3,000 tons per year equivalent will be suitable scale. And then we're looking at commercial offerings in 28, 29. So that's our broad pathway from here. And we're building a consortia around that for delivery at the moment. And then the last topic I was going to talk about was the biochar market. Now, we commissioned a biochar market in recent times, market assessment, and it identified over 50 beneficial uses for biochar. It also confirmed that Australia was a net importer of biochar, which is very interesting. The key, I suppose the key, or one of the key findings in that report in terms of maximizing the sale value of biochar is to achieve a biochar characteristics which are suitable for a particular market application. One of the comments, or one of the I suppose standout statements from that report was "char ain't char," and what I think what that really means is that biochar can be considered as an umbrella term, and biochar can have various different characteristics. The pyrolysis process in PYROCO, and Calpit went into some detail around this, because of the consistency of the temperature, we get a very consistent product out. And that product, because of low temperature pyrolysis, has a very high surface area, has very high moisture retention, and has a very high cation exchange capacity. So all of those characteristics make it very suitable for degraded soil improvements and many other applications. In terms of the potential applications that we've looked at the maturity and the value of various different applications. A lot of very interesting ones. I'll touch on a few perhaps. The adding of biochar to compost to accelerate the compost process has been very successful overseas, and actually the product sells for a higher price as biochar enhanced compost. There's examples of the use of biochar as a material in backfilling around street trees in the urban environment, very successful overseas. And again, I think it's also being adopted in parts of New South Wales to great success, reducing the watering requirements for those trees and enhancing tree growth. It's also some examples in Victoria around the use of biochar as a material for green roofs, and again, very, very suitable material for green roofs. On the industrial side of things, biochar has been used successfully as a part cement replacement in green concrete for non-structural concrete overseas. There's some very novel applications of biochar as a cement replacement for low temperature road pavement epoxies in Western Australia. Very interesting. And of course, all of these applications within industry can attract carbon credits. I'll probably leave it there, Dave, and wait for some Q&A questions.
Thanks so much, Eamon. Thank you for taking us through that. I can see that the Q&A is going well. Thank you so much, everyone, for putting their questions in there. I can see Calpit and Aravind been doing their best to try and keep up with those answers. So keep them coming. Also, too, I think as part of the webinar follow-up, we'll be sending a link to rewatch this or pass this link on to anyone else. We'll also look to address as many of these questions as we can in the Q&A. But we do have time for this. I will try and cherry pick and maybe combine a few themes here. So maybe if I go Calpit first, there's a few questions about the temperature of operation of the pyrolysis reactor, of the gas producer. Maybe can you describe those temperatures and why we're focusing on those temperature ranges?
Sure, David. I think I tried to answer that, but I'll just repeat again. I think the PYROCO reactor itself, the one which I've explained you, that's that we're planning to operate between 500 to 600 degrees centigrade. The outer side where we want to do combustion of oil and gas vapors, we're keeping that at around 100 or 150 degrees more, because when you have higher temperature on the outer side or in the tubes, the heat can be then transferred, the energy can be then transferred to the inside where the temperature is low. So you always need the temperature gradient. The gas producer, though we are operating at slightly higher temperature than PYROCO, because in gas producer we use air, and we try to produce oxygen-free producer gas. And when you have that temperature somewhere between 700 to 800, you get a good quality syngas or a producer gas, and that is also free of oxygen. So gas producer temperature we keep between 700 to 800, PYROCO temperatures between 500 to 600, and combustor adjacent combustor temperature of PYROCO we keep at 700 to 750, and then thermal oxidizer we finally keep above 850, and we provide 2 seconds residence time there, just to make sure that if any PFAS vapors are escaped from this whole PYROCO and gas producer system, are safely destroyed in the thermal oxidizer.
So Kalpit, if I can ask a follow-up question while I've got you here, and pulling together a few, some have been answered already, but also then, so through the process we are generating heat at this stage with some of the discussions we're having with dryer suppliers to hopefully return that heat into the drying process, and hopefully achieve most of the possible drying through that. There are some points where a little bit of natural gas will be applied to the process. Do you want to just briefly mention those and the kind of quantities roughly involved?
Sure. So if it all depends on whether you need any external energy or not. That depends on what is your feedstock, particularly what's the total solids content in your feedstock, as well as what's the total calorific value of your biosolid. So if your solids content is greater than 27%, and if your biosolids have a calorific value higher than 12 megajoule per kilogram, then PYROCO could run in thermal energy neutral mode. So that means that in that case, we won't need any LPG or natural gas. We still would need some LPG or natural gas, but that would be only during the startup. But once the plant's up and running, then we won't need any of those external fuels, as long as your calorific value is greater than 12 megajoule per kilogram and your solids content is higher than 27%.
So any requirement, Kalpit, for pilot lights for the thermal oxidizer or anything like that? Will that be necessary?
So generally speaking, as you improve the scale, David, then you could run with the very low pilot kind of LPG or natural gas type burners. However, what we found is that you could actually turn them off, but you need to have larger scale. So you need a lot more flux of the oil and gas vapors or that hydrocarbon vapors that could keep the flame going. At larger scale, we would not need it, but to certain scales, there will be always a pilot running, but pilot consumption. So imagine if in terms of the kilowatt thermal output from your system, if it's 200 kilowatt, you would be hardly needing maybe 5 to 10 kilowatt thermal energy in the pilot. So it's roughly around less than even 10%. So roughly around 5% auxiliary fuel.
Yeah, very low. Yeah, thanks, Kalpit. Now I'm going to ask Aravind a question. So I can see Aravind is very madly beavering away on answering some questions. So I'm trying to get his attention. Aravind, can you hear me?
Hi, David, I can hear you.
All right, good. Now that I've got your attention, I just want to, there's question in there about engagement with EPA on some of the PFAS results. So do you want to talk a little bit about the way we've engaged with the EPA in Victoria here and anything to share on there?
Look, thanks, David. So we've been working with EPA ever since this project got up in 2017. EPA sits in our project steering committee meetings. And EPA knows the data. This is a part of the R&D project for EPA. So we were obliged to share the data with them. So we shared the Mark 1 PFAS results with them. We were happy with Mark 1. And Mark 2, we haven't officially shared the report yet, but we are finalizing the report as we speak. But EPA is well aware of, I'm talking about WikiEPA is well aware of our project for the last few years. And part of the Biosolids Transformation Biosolids Center, the other EPAs are also involved in these type of projects from water authorities. So there's a huge interest from EPAs on this technology. I mean, any technology that will destroy or remove PFAS from biosolids. So keep in mind, beneficial use in agriculture is going to be difficult for all of us, some of us, at least for some of us. So we're definitely looking for alternate options, and thermal technologies is one easy way to do it.
Thanks, Aravind. While I've got your attention then, some other questions too about other type of contaminants. So do you want to maybe briefly mention the kind of things that we've analysed for at the Mark II scale and even the Mark I scale that we know have been destroyed through the process? So just some other examples to give.
So we use various labs to send biochar samples to test for pharmaceuticals, microplastics, and we in Mark I definitely we removed all pharmaceuticals and a bit of microplastics, but the Mark II microplastics data is still with the lab. So we looks like this demo technology will remove all contaminants from biosolids. So they're not really this current contaminants. We're talking about future contaminants like galaxolide, triclosan. Those other emerging contaminants will also be destroyed. I think our Mark III will do a comprehensive testing with all currently available emerging contamination list as well.
Yeah, absolutely. And so, yeah, from Mark I and Mark II, it's been quite a wide range of chemicals. So we're very confident that pretty much any chemical that's thrown at Mark II under those kind of conditions will be destroyed. So triclosan, for example, we've destroyed similar. So should be able to achieve that. Heavy metals is the one, and that is carried through, but that's what we talked about that earlier. Eamon, I might ask you a question, if I've got your attention, Eamon. Yeah, there we go. He's working on the questions in the Q&A too. So thanks, Eamon. I might ask you a question. Just if a water utility is thinking about their options now, what are the kind of things they should be thinking about? What should they be doing at this point in time to really, and what kind of horizons do they need to be working on?
Oh, thanks, Dave. Well, if we take our experience, understanding the biosolids in terms of its calorific value, its moisture content, its particle size when dried, those kind of characteristics of biosolids, which may not be part of a normal analysis when land application was the main game in town, is very, very valuable in terms of informing the drying and pyrolysis process. So that testing should start immediately, because of course the longer the data is available through different seasons and different years, weather patterns, is all very useful. Also good to look at the current biosolids storage management, whether there's clay beds, the risk of contamination in the future, because of course stones and volumes of clay as contaminants in biochar can be detrimental in terms of drying, certainly. And then in terms of funding and the cycles of funding that we go through, an idea of what the expectation of the cost looks like, and getting that within the normal 5-year cycle of capital plans. As I said, we've been on this journey since 2015. So in many ways, we've had quite a long journey to get to this point, and I think we could go into more prolonged conversations with utilities around our journey if need be. So we're always available for that.
Yeah, thanks, Eamon, for that. We're nearing the end, so probably we'll be able to slip in maybe 1 or 2 short questions, but please keep your questions coming into the Q&A. As I said, we'll do our best to come back to you with answers, perhaps a little bit more when we have a bit more time to add a few more sentences to those as well. Calpert, I'm going to direct this question. There's a few questions along these lines. So Calpert, if I have Calpert's attention, yep, good. Yeah, great to see you guys filling in the Q&A as quick as you can, which is great. Calpert, if you can come off mute, and I'll ask you, is there any particular limit on size and dimensions? Can you maybe talk about, you know, the relative scalability and footprint of the PYROCO reactor?
Sure. So just this, if some of you, if you have visited the PYROCO Mark II plant, it's kind of currently containing about 3 meter by 3 meter space without the need for, without dryer, but otherwise it contains everything else. So it has got thermal system, thermal oxidizer, as well as your back-end system like scrubbing and everything. So that's 3 and 3 by 3, but you could just say 5 by 5 meter. That's the space. And this unit, when you integrate it with dryer, could take between 1 to 3 ton a day wet feedstock. Now, if you go from that to say probably a 10 ton a day unit, which is almost 6 to 8 times kind of scale up, you could fit that everything in about 10 or 12 meter by 12 meter space. So PYROCO scalability, as it's a fluidized bed heat exchanger, when you increase the diameter, the volume increases in square. And that's why it's not a linear kind of footprint requirement. So as you go larger and larger, you need smaller and smaller footprints. So it will be very compact and relatively low cost at large scale.
Thank you, Calpert. Thanks again to our presenters and participants and attendees. Thanks so much for the questions there. I'm going to wrap it up here for today to make sure we finish in time. As I mentioned, we'll look to address the Q&A in a following mail out. We'll also look to send out a copy of the recording of this webinar. There's also, this is the second webinar we've done, so we'll include a link to that one as well. Also if any of you happen to be at Ozwater in Melbourne at the beginning of May, both East Water and Iota team will be there with a stand in the trade exhibition, so feel free to come along and have a chat about the technology there. We might even see if we can rope in Calpert on a day as well, and I think there also is a PYROCO related presentation within the technical schedule as well. Otherwise, off the back of the email that we'll send out, please feel free to reach out, and we'll put you in contact with the right people depending on the question and the project. So thanks again for your attendance. As Eamon said, now's the time to start thinking about your long-term plans. What's the business case you need around biosolids management? What are your thermal treatment options and the needs in your business? And starting gathering that basic information about your biosolids and your treatment processes, and really looking at which way to go. So as Eamon said, please feel to reach out, and we're happy to share anything on our journey in that space, and also what we're currently learning at the moment. So once again, thanks so much for joining us today, and we will sign off.